Welcome to the HeatWise tutorial on psychrometrics, part 1 out of 4. So in this one we'll just be going over what a psychrometric chart actually is, how to read a psychrometric point and all the relevant data from it, talking a little bit about the saturation curve, and looking at some movements on the chart from one point to another. So a psychrometric chart has lots of different lines on it, as you can see. The most important lines would be the vertical lines, which are different points on the horizontal axis. So you'll see here on the horizontal axis we have these numbers 35, 40, and so on. You'll see a 75 in the middle, all the way up to 120. So these are the dry bulb temperature lines. These are what you would typically see on a thermometer reading the temperature. This is what it would be representing, is the dry bulb temperature. And these lines extend from the bottom of the chart to the all the way through the top. So you can see here I've just highlighted the 75-degree dry bulb temperature line extending from the bottom up to the saturation curve. The grid of horizontal and vertical lines it consists of these dry bulb temperature lines and the humidity ratio lines. So humidity ratio is also known as absolute humidity, and that would be these values on the right side here, so 0.002, 0.004, up to 0.008, or sorry, 0.028. These are the lines for the absolute humidity, which is the pounds of moisture per pound of dry air within the saturated air mixture. So as the number increases, of course, the total amount of humidity is increasing. The other important lines here are the wet bulb temperature lines. So if you see on our saturation curve here, we have these numbers here, 35, 40, all the way up to 85. These are the wet bulb temperature lines, and these lines are actually diagonal across the chart. So if we take the 40-degree line, you can see how the line goes across the psychrometric chart. And it is the same angle for any of these lines. So you can see we've drawn here the 65-degree wet bulb temperature line. Most psychrometric points are defined by the intersection of the dry bulb and wet bulb temperatures. So if we draw here the 75-degree dry bulb line, we can see the intersection with the 65-degree wet bulb line is right here at this circle. And that would be the point defined by 75-degree dry bulb, 65-degree wet bulb temperatures. There are also other diagonal lines that are almost exactly parallel to the wet bulb temperature lines, and these are the enthalpy lines. So you can see here we have some enthalpy numbers, 15, 30, 50. These are BTU per pound of dry air. So you can see how close they are. I've drawn the 65-degree wet bulb temperature line right next to the 30 BTU per pound enthalpy line. With the enthalpy line in blue, you can see that these lines are almost exactly parallel, but they are actually just slightly off. The enthalpy of the air, that's essentially describing the total energy, internal energy that's actually contained within the air. And the final important line here would be the relative humidity lines. These are the curved lines. So you can see we have our 10%, 20%, and so on. Then we have our 90%, and then the final curved line is our saturation curve. So that would be this line right here. So the saturation curve is the point of 100% relative humidity. So anything above 100% relative humidity is impossible and will actually result in condensation within the air. So if you have surfaces that are a bit colder in the room, they'll condense before the saturation point. But if the air in the room becomes completely saturated, then water will be condensing on all surfaces in the room, regardless of their temperature. So one thing to note here is that as the temperature increases, the saturation curve goes up exponentially. So the air can actually hold exponentially more moisture as the dry bulb temperature increases. So for example, if we look at the 40-degree dry bulb line, it's a fairly low humidity, and the absolute humidity would be measured by drawing a horizontal line and seeing where it intersects that vertical axis. And I've also plotted here the intersection points of the saturation humidity with temperatures of 60 Fahrenheit and 80 Fahrenheit. You can see going from 40 to 60 Fahrenheit, we increase the absolute humidity at saturation from about 0.005 to 0.011. So it goes up by about 0.055. But then when we go again from 60 to 80, we get to about 0.022. So actually in both cases they're doubling. So you can see that exponential growth in the total humidity that can be held in the air as that temperature is increasing. So returning to that point that we plotted earlier at the 65 wet bulb, 75 dry bulb line, you'll see that it lies on the 60% humidity line. So this one point that was determined by two pieces of information, the dry bulb and the wet bulb temperature, we can read all of the relevant information. So we get our relative humidity, so that's the 60% point. We can see the absolute humidity, which lines up to about 0.011 pounds of moisture per pound of dry air. We can see the enthalpy, which will go to a little over 30, perhaps about 30.2 BTU per pound of dry air. And we can see actually our specific volume as well. So the specific volume lies on these other diagonal lines where you can see, for example, 14.5, 14, 13.5. These are the cubic feet per pound of dry air. So our value here lies at approximately 13.7 cubic feet per pound of dry air, and that's just the inverse of the density of the air, because as the air increases in temperature, it becomes more dense or less dense, but as the humidity increases, it becomes more dense. And one last important point here is if we extend the horizontal line all the way to the saturation curve, this will tell us the dew point temperature. So the dew point temperature here is about 60 degrees Fahrenheit, which means any surfaces in the room at this level of humidity that are at 60 degrees Fahrenheit or cooler will see condensation. So we'll start to get water condensing on those surfaces. And one important note here is that, as you can see, if we draw a line straight downwards from that dew point temperature, we will actually see the same dry bulb temperature. So we see a dry bulb temperature of 60 degrees Fahrenheit, which corresponded to our 60 degree Fahrenheit dew point temperature. And the reason for that is because at saturation, the dew point temperature and the dry bulb temperature and the wet bulb temperature are all the exact same value. So we hit all three of these temperatures approaching the same value as we get closer and closer to that saturation curve. When looking at translations on this chart from one point to another, say we had another point at 55, 60, approximately right there. If we moved from one point to another, say we moved from this original point to this second point, there's two forms of heat transfer. So we have sensible heat and latent heat to consider. Sensible heat refers to the horizontal translations on this chart. So in this case, you can see if we drew a dashed line at the same dry bulb temperature, we'd have a horizontal translation from 75 to 60 degrees Fahrenheit. So that's describing the just temperature or the energy related to simply heat in the air. And then we have our latent heat transfer, and latent heat is referring to the humidity. So we would draw a horizontal dashed line here, and we can see our latent heat would be the heat involved in going from our 0.011 pounds of moisture per pound of dry air down to about 0.076 pounds of moisture per pound of dry air. So this heat transfer process from point 1 to point 2, we'll call this one 2 and this one 1, is a loss of both sensible and latent heat. So there's both a decrease in temperature and dehumidification happening in a process like this. So anytime we're going right or left, that is sensible heat transfer. and anytime we're going up or down, that is latent heat transfer. So loss or gain of latent heat is referring to the increase or decrease of humidity in the air, and a loss or gain of sensible heat is referring to the increase or decrease of temperature of the air. And the one last piece of information to take a look at on this chart is right here where it says sea level. So this chart is actually calibrated for sea level measurements. So at sea level, the air is at standard atmospheric pressure, which is 1 atmosphere pressure, about 14.7 psi. So as the altitude increases and air pressure and density change with it, the numbers on this chart will actually change. So the curves will all start to change shape a little bit. The angles of the lines might change a little bit, but it will not be by very much. So most of the time, a sea level chart is acceptable, even if you're up to a few thousand feet above sea level. There is a certain level where it would no longer be acceptable, and there are other charts available. ASHRAE can provide charts going to 5,000, 10,000, and 15,000 feet above sea level. The vast majority of locations are less than 5,000, and the sea level chart would be an acceptable and mostly accurate chart, but as you're getting to higher elevations, you may want to consider using the 5,000 or even higher elevation charts. So that's it for this HeatWise tutorial. So for the next one, we'll be going over typical psychrometric processes and looking at how dehumidification, heating, and cooling all look on psychrometric chart, as well as air mixing and how to measure these values.